bonus points. We're going to get started. I want to show you that in your OneNote file under Test 4 Review, which Test 4 is on Chapter 5 and part of Chapter 6, I have some recordings of some of these problems already posted in your Test 4 Review. You can see here on the screen I have the Test 4 Review, and then on the right we have the links to videos from previous discussions. There was one up top there. Here's another one. And I think that might be it. So what I'm going to do now is, if you have any questions, you can type them into the chat bar, and I'll try and work those problems from the review for you. And otherwise, I'm just going to start working problems. So we can create another video to add to which problems are recorded here. I'll put the links here for people who couldn't attend this morning. So any questions to start with? Any items you'd like to see in particular? Just type it into the chat bar. Okay, the primary, I'm going to keep talking, and you can go ahead and type that in at any time. The primary focus of this chapter is on integration, the definite integrals, which correlates to the area under a curve. We start by looking at summations and using them to approximate these definite integrals. We discuss properties of definite integrals, and then as we go along, we're able to use the fundamental theorem of calculus to evaluate them, rather than having to use these limits of summations. All right, so let's start at the top. So item number 1. Hold on a sec. There we go. So item number 1 asks us to approximate. Let me make this a little bigger. We're going to use an approximation to estimate the area under the graph of a given function. And the function in this case is f of x equals x squared, and we want the area between that graph and the x-axis on the interval from 0 to 4. So I'm going to go ahead and draw that so we can visualize it. Okay, so x squared, you know, is a parabola, and it goes through the key points 0, 0, 1, 1, and negative 1, 1. Maybe I better make that a little smaller. 1, 1, negative 1, 1. But we want to go all the way out to 4 here, so way up here would be 4, 16. This is going to be a little out of proportion, but get the idea. Here's my parabola. Okay, and then on the interval from 0 up to 4, we want to figure out approximately how much area is under this curve. And the instructions tell us to use a midpoint sum with 2 rectangles of equal width. All right, so in general, if you have an interval from A to B and you want to divide it into n rectangles, then all you have to do is take B minus A and divide it by n to get the size of the base, which we'll call delta x. And in this case then, 4 minus 0 divided by 2 means each rectangle has a base of size 2. So Let's go ahead and indicate that on our graph. Halfway through the interval, we have the number 2, and you can visualize splitting up this interval. Now, in this case, we're going to take the midpoint of each interval, and we're going to use that to figure out the height of the rectangle. So the midpoint of an interval can always be found. Obviously, between 0 and 2, the midpoint is 1, but just so that you know, you're just taking the average of the two values. 0 plus 2 is 2, divided by 2 is 1. So you can do the same thing, 2 plus 4 divided by 2, 6 over 9. So the point 9 is where we're at the top of the second rectangle. Okay, so all they're asking us to do is to add up the size of the two rectangles and use that as an approximation for the area under the curve. So the first rectangle has a base. We always use base times height, right? So the first rectangle has a base of size 2. Well, they both do, really. Times the first rectangle, the y-coordinate is the height of the rectangle, so 1. Plus base times height again. The base has a size of 2 times the height turned out to be 9 for the second rectangle. So we have 2 plus 18 equals 20. So the answer to number 1 is C, or 20. All right, so that's what they mean by the midpoint sum. Now we could have also used the right endpoint of each interval to find the height, the left endpoint. It just, whichever endpoint of the subintervals they ask you to use, you plug that the function to get the height of each rectangle. So the area in yellow there is approximately 20. Okay, I'm going to skip number 2 because if you look over here, there's already an example similar to number 2 to help you out with that one. And I'm going to move on to number 3. So for number 3, it's called a Riemann Sum, basically. And what this represents is this symbol is the summation symbol. And it's telling us on the interval from 6 to 13 that we're going to add up, and you can think of this expression here as the height, and you can think of this delta x here, that's the base of, we're multiplying height times base of a bunch of rectangles. In fact, how many rectangles? N of them. And we're going to add that up. Now, as the base has a size going closer and closer to 0, what's going to happen is that's the same as n going to infinity, because this base getting smaller and smaller means we need more and more rectangles to fill the space between 6 and 13. So as n goes to infinity, what's going to happen is the number of rectangles is increasing, but we're also getting our approximation to be closer and closer to the area. And in fact, as n goes towards infinity, it's actually going to, the limit will equal the area. So that's what is happening in this expression here. Now, problems like this look really scary. They want you to translate this notation into one of these definite integral forms, but it's actually much easier than it looks. So all you need to know is A and B, which are the endpoints of the interval, and you need to know what function they're talking about. Remember, we get the height by plugging into the function, and what they've done is they've plugged in x sub k, x bar sub k into the function. So the function that they're talking about, just replace that with just an x, and you're talking about the function 3x to the 4th. So they're talking about on the interval taking the area between a and b of f of x dx. So replacing a with 6 and b with 13, and replacing f of x with what function it actually is equal to, 3x to the fourth dx, that gives you the definite integral version of that notation. So the answer to this one would be D. Okay, so whenever you see this very scary looking summation notation, remember you're just adding up the areas of rectangles, height times base. The base is always the delta x, and so the height is the function. And then the a to b is given you separately in the closed interval. Okay, so that's how you translate that notation. All right, now let's talk about some properties of this definite integral, which is just the area under the curve from, if it's a positive function, I should clarify. If this is a function that's above the x-axis, then this would represent an area. If it's below the x-axis, it would represent a negative area. If it goes above and below, we would get something called a net signed area. So it would be the, oops, I have this on ink to shape and I don't want that. We would get a net signed area, positive area plus the negative area on the whole interval. Everywhere we're below the x-axis, it's going to give us a negative version of an area. Everywhere it's above, a positive. And when you take the whole interval from A to B, you're going to get a sum. So it could add up to a positive or a negative, depending on if there's more area below or above it. In any case, we often break up these into pieces, these intervals, and deal with each piece separately. So as it turns out, if you break up an interval, for example, the interval from A to B of f of x dx, whatever I've drawn here, you could, if you wanted to, break it apart and deal with a to 0 of f of x dx and then 0 to b, and you'd still get the same total sum. My pen doesn't want to write for some reason. Let's see. There we go. But it doesn't have to be 0. You could break it up into any value, say d, anywhere in between a and b. So that's one of the properties of definite integrals. Another property is that it's really just a summation. So if you have, say, 2 times a function, then that's the same as you're going to have twice the area, right? So that would be the same as 2 times the definite integral representing the area under the original function. So let's look at this particular example, item number 4, and discuss some of the properties here. So they're saying, suppose that f is a continuous function and we're looking at the definite integral from -4 to 4, and it turns out to equal 0, which tells you that the total area above the x-axis and below were the same. So when we added up the negative and positive areas, we got 0. And then they're also telling us that for that same function, the interval from -4 to +7 has an area, a total net signed area of 4. And they want to know if, using that information, can we find the definite integral negative integral 4 to 7 2 times f of x dx. Okay, so one thing I would observe is that this is going to be the opposite of 2 times the integral from 4 to 7 of f of x dx. And so I would ask myself, do I have information about the integral from 4 to 7? Well, we don't, but we have the integral from -4 to 4 and the integral from -4 to 7. So thinking about a number line, from -4 to 4, the area adds up to 0. And from -4 to 7, the area adds up to 4. So that means that this piece between 4 and 7 had to have been contributed an area of 4, right? So we know that this, by subtraction, in other words, we can take the integral from -4 to 7 of f of z dz. I don't know why this is z's and this is x's. I guess they're just trying to emphasize that it doesn't matter what that independent variable is there. But anyway, the integral from -4 to 7 minus the integral from -4 to 4 is actually going to give you the integral from 4 to 7. Okay, so that means that 4 minus 0 is equal to 4. So coming back up to what we needed -2 times that value. So that's -2 times 4, which is -8. So that's the answer, item D, -8. So that's in the section using properties of definite integrals. Okay, now let's move on to the next exercise, which is item number 5. And we're going to, by the way, good morning, Letley. Nice to see you. We're going to use the definition of the definite integral to evaluate the integral from 1 to 6 of x squared minus 1 dx using a Riemann sum. Okay, so again, the idea of a Riemann sum is that we're adding up a bunch of rectangles, and we're going to take the limit as those rectangles get smaller and smaller, or in other words, as the number of rectangles goes to infinity. Now in number 5, oh yeah, they have 2 parts. So first you have to select which one of these summations represents the correct Riemann sum, and then you have to actually go and evaluate it. All right, so in the first part, writing the Riemann sum, we usually use the right-hand endpoint. I want to see if they actually did. Let's check it out. All right, so if we take the interval from 1 to 6, and remember we've got some function up here. Actually, it doesn't look like that because it's x squared minus 1, but in any case, it might be something like this on the interval from 1 to 6. But what we're wanting to do is to divide it up into n subintervals. Remember I told you that the base of the subinterval, the base of the rectangle, I should say, is going to have a size we refer to as delta x. Now, in a Riemann sum, is not necessary for each of the bases to be the same size, which is why they say delta x sub k instead of delta x, because for each kth subinterval, they use a different notation. But for the purpose of calculation, it's way easier usually to have them be the same size. So we most of the time will use b minus a over n, the size of the interval divided into n rectangles. In this case, that would be 6 minus 1 over n, or 5 over n. So you can see that 5 over n, it pops up in C and D. So we can already eliminate these 2 options here. All right, and then beyond that, what we like to do then is what I like to do is usually to use the right endpoint. I'm not sure if they did use the right endpoint, but let's see. So what I mean by that is you take your starting point, and which in this case would be 1, I refer to it as A, and you're going to add to it the size of the base, the delta x, 5 over n. But then for the next one, you're going to add 2 times 5 over n, and then 3 times 5 over n, and so on. So the way we write that is a plus I times delta x. That gives you the the right endpoint of each one of the rectangles. So in this case, a is 1 plus I is going to change. 1 times delta x, 2 times delta x, 3 times delta x, and then times delta x. Now they don't appear to be using I, they're using k, so I'm going to switch my index. Doesn't matter what letter you use there. It's just an integer. K times 5 over n. Okay, so the right endpoint, the x coordinate will be 5k over n plus 1. Right, if k is 1, that's 1 plus 5 over n. If k is 2, that's 1 plus 10 over n, and so on. And that's going to give you each one of these x coordinates. But remember, the height of a function is not determined by the x, it's the y. So you have to plug that into whatever function you have. So looking back at our definite integral that we were given, the function is actually x squared minus 1. So to get the height, we're plugging into f of x equals x squared minus 1. So if you plug this into that function, you're going to get 1 plus 5k over n squared minus 1. So this is the height, and then you multiply it times the base of the rectangle, 5 over n. You add all of those up and take the limit to infinity, and you get your integral. And so it looks like that would be D, where we see that summation. Okay, now how do we use that to actually evaluate the integral? We have to take the limit as n goes to infinity. And I kind of take issue with this question because I think they should have written limit as n goes to infinity here. But anyway, let's go ahead and I'm going to write this down off to the side so we can evaluate that limit. All right, so we're going to evaluate the limit as n goes to infinity of the sum k equals 1 to n of, and then we have 1 plus 5k over n squared. Let me know, by the way, if you're having any trouble hearing me or anything, you can type it into the chat bar. And then minus 1, and then times 5 over n. So the algebra is a little bit of a pain, but the limit's actually not too bad. So what we're going to do is I'm going to square this out. So we're going to have limit as n goes to infinity, sum k equals 1 to n of, and then we're going to have, let's see, that's 1 plus 10k over n plus 25k squared over n squared. If you square that out, and then minus 1, oh, that's nice, the 1's are going to cancel out, times 5 over n. Cancel, cancel. Okay, and then we're going to take the limit as n goes to infinity of the sum k equals 1 to n. I'm going to distribute the 5 over n to each term. So we're going to have 50k over n squared plus, and then we're going to have 125k squared over n cubed, and then that's it. And then we're going to break this apart. One thing about a summation is just adding up a bunch of terms. So if you have summation if you have a sum inside the summation, you can break it up into 2 summations. So we're going to take the limit as n goes to infinity, the sum k equals 1 to n of 50k over n squared plus the sum k equals 1 to n of 125k squared over n cubed. Okay, and then we're going to also observe that when you have a summation, any constants inside of it can be factored to the front of the sum. So in this case, for example, 50 and n are constants. They're not varying. K is varying. K is going from 1 to n, but for the purpose of this summation, n is fixed. So we're going to bring 50 over n squared out front. and leave inside the k equals 1 to n. We're going to leave inside there the k. Plus, here we have the sum k equals 1 to n of 125 over n cubed times k squared. So I'm going to factor out the constants again, 125 over n cubed times the sum k equals 1 to n of k squared. Okay, and then we need to use the formulas for the summations. So the summation formulas for the sum k equals 1 to n of k is going to be k times k plus 1 over 2. And the summation formula just want to make sure I'm writing this down correctly. The summation formula for k squared is equal to, k times k plus 1 times k plus 2. I'm sorry, 2k plus 1. See, I always do that. 2k plus 1 over 6. Okay. So we are going to have, in replacing, oh, I wrote k's instead of n's. My bad. Sorry. N is getting plugged in there, so this should have been n times n plus 1 over 2, n times n plus 1 times 2n plus 1 over 6. Okay, so we're going to replace each of these summations with what they are equal to. So we're going to have the limit as n goes to infinity of 50 over n squared times n plus 1 over 2 plus 125 over n cubed times n plus 1 times 2n plus 1 over 6. Okay, now this looks really messy, but keep in mind, first of all, we can take the limit of each part and add it together as long as they each are limit is a finite number. And also, when you have a rational expression like this, really all that matters is in the numerator and denominator, what's the highest degree term. So for example, in this first one, if I were to multiply this out, I'd get n squared plus n. And then if I distributed 50, the first term with the highest degree in the numerator would have 50n squared. And in the denominator, 2n squared. There's more stuff there, but that's not going to affect the limit to infinity. Only the highest power dominates. And then the same thing here, if I multiply n times 2n, I would get the highest degree term here. N times 2n would be 2n cubed times 125 would be 250n cubed. And then there would be a bunch more other terms, but that would be the highest degree term. And in the denominator, we'd have 6n cubed. And so the limit to infinity, as n goes to infinity, is just going to be the ratio of the coefficients of the highest degree terms. So 25 here, and let's see, does 6 go in evenly? I don't think so. So this one, let's see, we can reduce it though to 125 over 3. So the limit is actually going to be 25 plus 125 over 3. Let's see, 25 is 75 over 3, so this is going to be 200 over 3. So that would be the actual area, 200 over 3. Okay. Again, if you have any questions, type it into the chat bar. Okay, and then on item number 6, I have time for one more, so I'm going to do item number 6 unless somebody wants something else done. On item number 6, it just says evaluate the integral. Now, it's true that we could set up the integral using a limit of a Riemann sum, but when you're not told to do that, it's much easier to use integration formulas. In particular, this one, the integral from 1 to 4, I'm going to think of this as t plus t to the negative 1 dt. Okay, we have a rule that says the integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. But when you're evaluating a definite integral from a to b, you don't actually use the plus c. You plug in the top limit, you plug in the bottom limit, and you subtract. So that's how we're going to deal with this particular exercise. So thinking of t as t to the first power, we're going to use x to the n over x to the n plus 1 over n plus 1. So that would give us t squared over 2. But now we would run into a problem if we tried to use this rule for this guy, because that would give us division by 0, right? We'd have t to the 0 over 0, which doesn't matter. But we have another integration formula, the integral of 1 over x dx, or the integral of x to the negative 1 dx, which is the natural log of the absolute value of x plus c. So we would then use that integral rule for this one, and we would have the natural log, the absolute value of t. And then, oh, I'm sorry, I didn't realize this is squared out. Gonna have to start over. Okay. We gotta square that first. You cannot just work inside the parentheses without squaring first, so my bad. All right, so we're gonna square this out, so we're gonna FOIL. So this is gonna be the integral from 1 to 4. And then we're going to have, let's see, t times t is t squared. T times t to the negative 1 is just going to be t to the 0, which is 1, and we're going to have that twice, so plus 2. And then t to the negative 1 times itself is going to be plus t to the negative 2. Okay, dt. Oh, so in this case, we actually won't have a 1 over t anymore, so we can use the power rule twice. All right, and so the integral from, well, actually we don't need to write the integral symbol as soon as we start applying the rules. So the integral of t squared, you're going to add 1 to the exponent and divide by it, plus we're going to have 2 times t. The integral of a constant, you always just slap the variable on there, because if you think about it, what's the derivative of 2t? It's 2, and integration reverses derivatives. So, and then plus add 1 to the exponent, t to the negative 1 over negative 1. And normally we would put a plus c, but this is being evaluated from 1 to 4. So if we put plus c and we do our subtraction, it's just going to cancel out anyway. Oops. Okay, so now we're going to plug in, always plug in the top bound first. So that's going to be 4 cubed over 3 plus 2 times 4 plus 4 to the negative 1 over negative 1. And then we're going to subtract from that 1 cubed over 3 plus 2 times 1 plus 1 to the negative 1 over negative 1. Okay, so this is going to give us 64, is that right? Yeah, 64 thirds plus 8 plus 1, oh, minus 1/4 actually. And then on the right here, we're going to have negative, I'm going to do negative as I go. It's going to be negative 1/3 minus 2. And then that would be a negative 1 at the end, but I'm going to change it to a positive 1. Okay, and let's see. 60, I like to combine the ones that have common denominators first. So 64 thirds minus a third is going to be 63 thirds. And then we have 8, and negative 2 is 6, and 1 is 7, plus 7 minus a fourth. Now 63 thirds is 21, so 21 plus 7 is 28 minus a fourth. 28 minus 1/4. So I mean, that's 27 3/4, but we would normally give our answer in a mixed number. So let's see what this is gonna be. 4 times 27 would be 80 plus 108 plus 3 is 111. So 111 fourths. So that's gonna be answer B. Okay, I'm gonna have to stop now, but remember, you can send me your Ask My Instructor questions. If you're not receiving an answer to my Ask My Instructor question, just send me an email through Canvas and let me know, and we can figure out why that might be, because I do prioritize those questions. So they either, went to my junk mail, or perhaps you're checking a different email than the response is going to. So do get in touch with me. You're not bothering me. And also email me if you have any other concerns that I can help you with. We're finishing up the semester now. So let's see, let's look at our